Okay, let's now have Helena Lopes from the Universidade Federal do Rio de Janeiro.
Thank you, Ricardo. I'd like to thank the organizers for the invitation, especially the scientific committee for the invitation to give a talk here. Microphone is not working?
Not really.
Uh-oh.
Então, esse esse? Oh.
Should I remove this one?
Não, esse aí é daquele liga isso.
Não, esse é
O da lateral é só para gravação.
Ah, daquele liga isso. Se eu soubesse ligar, ajudava, né?
Não é esse aqui não, Ricardo?
Não, esse aí não. Esse foi.
Então, tira esse.
Não, esse é do computador.
Tá.
Esse é do computador. Não precisa, acho que pode deixar aí.
Hello. Okay, can everybody hear me now? All right, okay. So, yeah, my name is Helena and Sezekelyhidi, and I was an undergrad here at PUC and a master's student here at PUC under Carlos Tomei's supervision. I first met Carlos when he was freshly arrived from Yale University. He taught a class on complex variables in my last year as an undergrad, and the class consisted of two students, myself and my husband, Milton Lopes. We had a ball. It was a very intense class. There were lots of Carlos pearls during the class that we remember today, till today. You know, the proof, Carlos' proof of the Riemann mapping theorem was flip, 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 flip. Carlos augmented my vocabulary. I learned the word amanuense in the amanuense theorem, the accountant theorem. We learned about the Schwartz lemma, the mathematician with no vowels. Okay. And at the very end of the class, we earned our carta de alforjes Rio. Rio. That was one of the pearls. Okay. I also remember once we were on the bus back home, Milton and I, and Carlos pops in the bus, and he looks at us and says, "Oh, hi class, let's go for a juice."
Let's continue.
Yeah. So after this class, I graduated from my undergraduate education, and then I became Carlos' first graduate student. He was his master's student. And overall, it was a very traumatic experience. Carlos was very tough. Okay, Carlos was really, really tough. But I also should say that a lot of the complaints, the criticisms, and things that I heard from him back then helped shape me up as a mathematician today. Okay, so I owe you a lot. Thank you very much. Okay, so the title of my talk is a paraphrasing of a book that Carlos used to talk a lot about. It was a brand new book back then, Au-delà des opérateurs paradifferentiels, ou para lá de pseudos, as he used to say. So this is beyond the resolution of the Onsager Conjecture. Okay. All right, so I'm going to start with this PDE, or actually the system of PDE. The equations modeling incompressible fluid flow. This is a system. Okay, U is a velocity vector field, and P is a scalar pressure. So if you're in 2D, you have three unknowns here, the two components of the velocity vector U, and then the scalar quantity P. And if you're in 3 dimensions, you have 3 components of the velocity vector U, and plus the P. So this is either a 3 by 3 or a 4 by 4 system augmented by this divergence U equals 0 incompressibility condition. So here's the system UT plus the differential operator U dot grad, the formal differential operator U dot grad applied to each of the components of U. That's equal to minus the gradient of pressure plus this blue term, nu Laplacian u, plus a forcing term f. Nu Laplacian u is there if you're doing Navier-Stokes. It's not there if you're doing Euler, if you're talking about Euler. So Navier-Stokes is a model for real-life fluids, viscous fluids. Nu equals 0 Euler equations is a model for these ideal or perfect fluids that don't really exist in the universe, but that are in approximation when you can neglect viscosity. Okay, let's do a very easy calculation here. Let's hit the equations with u. That means take the inner product of the equations, the evolution equations by u, and integrate over space. And I'm going to assume that I have no boundaries, so either the flow is periodic or in the full space. And so I can write this as the time derivative of 1/2 of the integral of u squared. And here's my right-hand term. I put all of these terms on the right-hand side, took the inner product with u, and then I used the divergence-free condition to rewrite each of these terms as an exact derivative minus nu times the integral of the gradient of u squared. This is my viscosity term plus the work term u dot f. This is the work term, and this is actually the kinetic energy because the density here is 1. Okay, so this just says that in the absence of boundaries, and for smooth solutions, the time derivative of the kinetic energy is equal to minus viscosity times the integral of the gradient of u squared plus the integral of u times f. This integral of u times f is the work. This is the dissipation of kinetic energy term, or the dissipation term, the dissipation rate term. Okay, so what we learn from this is that if you have a smooth inviscid fluid flow, then it satisfies balance of kinetic energy and work. Okay. However, the flows that I'm going to be interested in are closer to turbulent flows. And for turbulent flows, it's postulated that you should have anomalous dissipation, okay, or inviscid dissipation. These are two related phenomena, and I'm going to explain to you what is each. So anomalous dissipation means that the dissipation rate doesn't vanish when viscosity vanishes. And it's a cornerstone of turbulence theory, also known as the zeroth law of turbulence in Kolmogorov's 1941 theory of turbulence, which I will get to in a minute. Inviscid dissipation is related to this, but it refers to solutions of the inviscid equations. It doesn't refer to the limit of vanishing viscosity. It refers to the inviscid solutions. So it simply means that the inviscid fluid flow doesn't satisfy the energy balance. No mention of whether energy decreases, increases. It simply is not conserved. Okay? Now, turbulence, therefore, requires anomalous dissipation, and therefore you're talking about rough flows. You're talking about non-smooth flows. Okay, in 1949, Onsager proposed the following conjecture, that inviscid dissipation could happen if the flow was less than a third regular. Okay, and I'm going to get into that in the rest of the talk. Whereas if you have more than a third regularity, inviscid fluid flows conserve energy or balance energy if you have a forcing term. Okay. Research developed along two different directions, one called flexibility, the other called rigidity. And flexibility simply means trying to obtain rough fluid flows that don't conserve energy. Okay? Rigidity means trying to establish what is exactly the regularity threshold, which implies energy balance. Okay, so let me tell you a little bit about K41 according to Uriel Frisch. So K41 is the Kolmogorov theory of homogeneous isotropic turbulence. Back from 1941, there's been a number of corrections over the years, but this is still really the paradigm. Okay? So I will tell you two of the three hypotheses from K41. Hypothesis H2 is a scaly invariance, that the turbulent flows is assumed to be self-similar with some kind of self-similarity exponent h. Okay, so the velocity increments go like lambda to a power h times the velocity, well, when you scale by lambda, okay, in space. And that there would be finite energy dissipation in the vanishing viscosity limits. So a turbulent flow will have a finite, non-zero kinetic energy dissipation rate per unit mass, minus the time derivative of the kinetic energy should converge to some positive epsilon when viscosity vanishes. Okay, this is a phenomenological theory of turbulence, and this has only been proved by experiments. There's no analysis to back this up yet. Okay? All right, so the Onsager conjecture took K41 plus scaling plus dimensional analysis to arrive at the conclusion that the self-similarity exponent should be exactly a third. Okay, so this is roughly equivalent to having a Holder exponent a third. Now, the natural question is a third regularity plus Navier-Stokes enough to produce anomalous dissipation? We still don't know that. Okay? What is the regularity threshold that does imply energy conservation? So again, the Onsager conjecture, a little bit more precisely, states that inviscid fluid flows that are Holder continuous with exponent greater than a third conserve energy, whereas if the exponent is less than a third, it should be possible to find inviscid fluid flows that dissipate energy, or at least that don't conserve energy. Okay? Okay, so here's a picture of the man, Lars Onsager, ladies and gentlemen. He was a Norwegian and American chemist and a physicist who won the Nobel Prize in chemistry. But he wrote many influential papers in chemistry and physics, and also in fluid dynamics, and in particular in turbulence. He made a big name for himself. This is the first page of the famous article. It's a very short article in Nuovo Cimento, Statistical Hydrodynamics. And here is the last page, the last paragraph of his 1949 paper, where I will read to you the highlighted portion. In principle, turbulent dissipation as described could take place just as readily without the final assistance of viscosity, i.e. inviscid dissipation. In the absence of viscosity, standard proof of conservation of energy does not apply because the velocity field doesn't remain differentiable. In fact, it is possible to show that the velocity field in such ideal turbulence cannot obey any Lipschitz condition. He calls it a Lipschitz condition. He's a physicist or a chemist. It's actually a Holder condition of the form velocity increments less than r to a power, spatial increment to a power, for any order greater than a third. Otherwise, the energy is conserved. Okay, so this is the Onsager conjecture as it became known. Onsager's argument to arrive at this is brilliant. It's simply dimensional analysis. Okay? He noted that the relevant term is the flux term of energy, which is a term u dotted with u dot grad u, which should be zero. Okay? It should integrate to zero. Okay? At the very least, it needs to be bounded. So if you look dimensionally, u times u dot grad u is basically u cubed over L. So for that to be bounded, you have to have u basically Holder continuous with exponent a third. That is the proof of the Onsager conjecture according to Onsager. Okay, so done? No. Let me tell you what happened to this. So the first results go back to a paper from 1993 by Vladimir Scheffer. It was a completely incomprehensible paper on incompressible fluid dynamics, where he showed the existence of a vector field which was L2 in space and time, which didn't conserve energy. Okay? And essentially, I'm sorry?
There's quite some time between Onsager and...
Yes, that's where things started, in 1993. That was the first example. So Scheffer's example is a solution which starts being zero, then it appears all of a sudden it's non-zero, and then it goes back to being zero. It's compactly supported in space and time. Okay. Then Sasha Schneermann in 1995 took this example and turned it into something comprehensible. He was inspired by this notion that of the inverse energy cascade, where energy goes from small scales, the direct energy inverse energy cascade, where energy goes from small scales to large scales. Okay. And he built an example using this intuition, again, compactly supported in space-time. However, it's not in the physically natural space because the velocity is not L infinity L2, it's only L2 in space and time. It's only square integral in space and time. Okay. And then finally, in 2009, there was a breakthrough result by Camilo DeLellis and Lars Onsager Yeah, I guess in this field you have to be able to pronounce people's names, this name in particular, to work here. Okay, so what they did was to produce an example of a velocity field which is bounded. In fact, it's not only bounded in time into L2, but it's actually bounded everywhere. Okay, and it's compactly supported in space and time, and it solves the Euler equation. So you start from 0, then solution bubbles up from nowhere, and then it goes back to being 0. Basically, I heard an analogy once in a conference. This was Idris Titi saying, it's basically as though you pour yourself a glass of water, go to sleep at night, you pour yourself a glass of water, put it on your bedstand, you wake up in the middle of the night, you think that you're having a nightmare because all of a sudden the water is bubbling up and down, and then you go back to sleep and you wake up and everything is fine again, the water is stopped. Okay, so that's basically what this solution looks like. Okay, now this proves non-uniqueness for the weak solutions of the Euler equations, but it also was the beginning of this Onsager conjecture endeavor, the true beginning. Okay, because before, Schaffer and Schulman's were interpreted more along the lines of non-uniqueness, plain non-uniqueness. Okay, so you have a time-dependent energy. And the reason that I'm calling Camillo and Laszlo's work a breakthrough is because they introduced, for the first time, the tool of convex integration applied to fluid dynamics. Okay, and this has been an incredible journey since then. Okay, so things moved on. Eventually, they managed to fine-tune their example to get a continuous solution, and then they got a Holder continuous solution in C0 1 over 10. Okay, the exponent was 1/10. Then there was another breakthrough by Phil Isett from 2013, which was later followed by work almost same year actually. Well, they obtained it the same year, but they published it later, by Tristan Buckmaster Camillo, who was a student of Laszlo and of Camillo, and Isett also, where they produced a solution which was C0 almost 1/5. Okay, and then in 2016 they wrote a paper where they got a solution which was L1 in time into the Onsager critical space C0 1/3 minus epsilon. Okay, and from there on, okay, things were sort of stalled because up until between 2009 and 2016, one was scared to open archive because you opened archive and there was a new paper there almost every day. Okay, it was ridiculous. Okay, then things got stuck. People were stuck. They didn't know how to get past this L1 in time barrier, and that was until Sara Daneri and Lars Sezekelyhidi's work on Mikado flows, which then Phil Isett fine-tuned into a full proof of the Onsager conjecture. So, in theory, the Onsager conjecture is proved. I don't really like their proof because it's very ad hoc. It's not a vanishing viscosity limit or anything like that, but there it is. There exists inviscid dissipation in the correct Onsager space 0 1/3 minus epsilon. That was from 2018. In 2019, Tristan, Buckmaster, Camillo, Laszlo, and Vlad Vikol showed that they could produce an Onsager critical solution with any prescribed energy profile. So you give me an energy profile, and I'll find you a solution with that energy as its energy. So this is pretty big. Okay, then another breakthrough in 2019 by Tristan and Vlad. They produced inviscid solutions which were vanishing viscosity limits. However, these solutions with any prescribed energy profile, however, this inviscid limit has bad regularity. Okay, the viscous solutions have bad regularity. They're not Leray-Hopf solutions. They're not L2H1. They were only L2H1 half dot. Okay, so they were in these critical spaces. So it's a great result, but it's not what we're aiming for yet. Okay. Also, I should mention that basically since the 2013 paper by Isett, everything that follows here is really a 3D construction. It could not be adapted to 2D. Okay, so there was no 2D Onsager conjecture proved. although the exponent is, the critical exponent is still expected to be 1/3 because the dimensional analysis is there to tell us that. Okay, in 2021, Elia Brouet and Maria Colombo showed non-uniqueness for 2D Euler with a vorticity, which was in this Lorentz space, weak L1. Okay, that was a pretty big deal because, again, so vorticity is a physical quantity, a very important quantity in incompressible fluid flow, and all of the previous constructions were way too irregular to talk about vorticity. Okay, so this is the first paper in that direction. And then here's another breakthrough paper from 2021. Dallas Alberton, Elia Brouet, and Maria Colombo showed non-uniqueness of Luray-Hopf weak solutions for Navier-Stokes, but with a very rough forcing. So again, it's open with zero forcing. This is not a convex integration construction, so I like it better. And it's based on, it builds on work by Mishavishik from 2018. Mishavishik in 2018, he put a paper in the archive where he shows non-uniqueness for 2D Euler with LP vorticity for large P's, but with rough forcing. Well, it's a two-part paper. It's maybe like each part is like 50 pages or something, and it's written in Word. So it was never submitted, I swear. Okay, so since 2021, what's happened? Many more results using convex integration. This has been an incredible journey. The flexible Onsager result, in other words, the Onsager conjecture in 2D, was finally proved last year by Vikram Giri and Radu. In 2023, Matt Novak and Vlad Vikol produced examples of inviscid dissipation in L3-based spaces, which was also a really big deal. And last year, there was a really, really outstanding new result, non-uniqueness for 2D Euler with vorticity and LP. For some p larger than 1. We thought that this was not possible. This means that the velocity field is W1p. It's a lot more regular than we ever expected it to be. Okay, and then this year I heard in a conference I was in last week that Alexei Sheskinov and Mimi Dai managed to fine-tune Elia, Maria, and Anuj's result to get a better p. Their result required a new formulation of convex integration, whereas Alexei and Mimi managed to find it with the standard convex integration. And finally, this is also part of the result of this conference from last week. Dallas Alberton, Maria Colombo, and Giulia Mascolini proved non-uniqueness of vanishing viscosity solutions for 2D Euler with LP vorticity for some p greater than 2. But this is with, again, forcing, with a rough forcing. And what they're doing is basically doing a perturbation argument on Vishik's result. So Vishik, his paper was never published. He never submitted it for publication. He just put it on the archive. But then Camilo and Laszlo did a reading seminar in Princeton a couple years ago. And there's a paper, a 7-author paper. Basically, it's Camilo and all his students, and some postdocs, and Maria Colombo also, where they actually went through Misha's construction in detail and fine-tuned it and refined it and even improved a little bit upon it. Okay, so this is a big deal. All right, how does convex integration work? So the earliest results amount to substituting the Euler equation for a differential inclusion. You start with some kind of subsolution and you start adding oscillations. You start adding a whole bunch of ad hoc oscillations, and you remember the Riemann-Lebesgue theorem, which says that oscillations go weakly to 0. Okay, so they are small amplitude and large frequency oscillations, and you add them and push your subsolution to the boundary until it becomes a solution. Okay, and you have this convex hull of solutions. All right, so this led to the first results along the lines of the Onsager conjecture, but that wasn't enough. You needed better estimates in order to get this C1/3 regularity. So nowadays what people do is they add certain better oscillations. Basically they add a perturbation called WQ, which is small amplitude and supported on large frequencies, but which is carefully chosen. Usually you use something like a Beltrami flow or a Mikado flow, something that is a stationary solution of the Euler equations in order to cancel the Reynolds stresses on your right-hand side. Okay, you then take the limit as the frequency goes to infinity to get a solution by convex integration. That is the method of convex integration. Okay. The idea of convex integration comes from this Nash-Kuiper theorem from geometry, where one proves that the unit sphere in Rn can be isometrically embedded into a ball of radius arbitrarily small, epsilon. You can crumple a piece of paper and downsize it to as much as you want, as close to a point as you want, through a C1 embedding. Okay, flexibility allowed by the C1 embedding is a key fact. C2 wouldn't work because you need very large curvatures in order for this to work. So basically that's the same thing that you're doing, but in fluid dynamics. Okay, let me talk a little bit about rigidity. In other words, to find the regularity threshold for energy balance, and let's look first at the case of zero forcing. The first results in this direction came a little bit earlier than Scheffer's result. They were due to Uriel Frisch and Pierre-Louis Soulem from 1975, and they proved that if the flow is bounded in time and h5/6 has 5/6 of the derivative in space, then the flow is rigid. In other words, you have conservation of energy. This refers to solutions of the Euler equations, so inviscid fluid flows. Okay, then in 1994, Gregory A. Inc., and then Peter Constantin, Winan E., and Idris Titi, they refined A. Inc.'s result, and they proved that if the flow is power 3 integrable in time, and in this Bezov space, b 1/3 plus epsilon 3 infinity, which basically means 3 1/3, okay, then you have a conservation of energy. Okay. The state of the art, because they can't get all the way down to b 1/3 3 infinity, is due to Alexei, Peter Constantin, Susan Friedlander, and Roman Shvitkoy from 2008, and it says that if the flow is L3 in time, b 1/3 3c0, then you have conservation of energy. Okay, so b 1/3 3c0, for those in the know, mean that the Littlewood Paley components vanish at infinite frequency. Okay. These are all 2D and 3D results. Anything that pertains to Bezos spaces doesn't really see the dimension. A generally 2D result is due to Duchamp and Robert from 2000, and they showed that if the initial vorticity was in LP for p greater than 3/2, then you have conservation of energy. And notice here that this is initial vorticity. In other words, the only condition is on the initial data, okay, not on the solution. The previous results are conditions on the full solution. Okay. And the extension to p equals 3/2 follows from Sheskidov, Constantin, Friedlander, and Shvitkoy, because the velocity field is then L3 in time, W1 3/2, which is contained in this space, L3, B 1/3 3C0. Now, on the physicist side, Kreisman came up with a 2D turbulence theory, which would be the K41, but for 2D, which postulates a forward entropy cascaded, a direct inverse energy cascade, a forward entropy cascade, and this suggests that there's a regularizing effect in 2D that is not present in 3D. Okay? So it suggests to us that there could be a dynamical mechanism to avoid anomalous dissipation in 2D, even for so-called supercritical flows. So before I get into that, I have to tell you a little bit about what is criticality in this case. So the energy flux, which is the key object here, is the integral in space and time of u times u dot mod u. And its dimensions are u times the greater of u, which is u over L, length scale, times length scale to the power n is a dimension of my space, times time. In other words, u cubed, L to the n minus 1 times time. And so based on this observation, Roman Shvitkoy introduced the Onsager critical spaces, where a Banach space is Onsager critical if the cubed of its norm scales exactly like u cubed L to the n minus 1 times time. So I'm going to tell you some examples of Onsager critical spaces in 3 dimensions: L3 in time L 9/2, and L3 in time H 5/6. In 2D, L3 in time L6 in space, L3 in time W1 3/2 in space. And in any dimension, L3 in time, W1 W1 third 3, and L3 in time B 1/3 3P for any P between 1 and infinity. All right, now in these spaces that are in these boxes, these colored spaces, that is where conservation of energy has already been established. With the caveat that in 2D, you could actually exhibit solutions which do live in L3 in time. Okay, so now I'm going to particularize everything to two-dimensional flows. So I'm looking at 2D Euler on the torus. I don't want to have to deal with boundaries. Okay? And I'm initially interested in weak solutions for which the vorticity is pth power integral of some p greater or equal to 1. Okay, this is a reasonable assumption. This kind of estimate is preserved by my flow. And while solutions are typically too weak to talk about integrability of vorticity, however, first example with control on integrability is the one that appeared in October of last year, October of last year. This paper that I mentioned by Elia, Maria, and Anuj. And also this year, there's a paper by well, not a paper yet, at least an announcement of a result by Alexei and Mimi with a still bigger p, even bigger p. So bigger p's are more challenging. Okay? The bigger the p, the less rough your solution. All right, so here is a baseline definition of a weak solution, and it's basically you hit your equations by a test vector field, which is divergence-free, and place all of your dangerous derivatives on your test vector field. And the divergence-free condition should be satisfied in the sense of distributions. Existence of weak solutions in 2D is known for vorticities in LP. Could be larger than 1. This goes back to the work of DePerna and Maida from 87. There was also the work in L1 of Italovecchi and Cedro from 1993. Uniqueness is only known in L infinity and nearby L infinity. In non-uniqueness, there's been a lot of recent work on non-uniqueness. There is the work by Vishik that I mentioned, the Word paper for vorticities in LP for some large p, but with a non-trivial forcing. Here they are, the seven authors. Dallas Albritton, Elia Bruet, Maria Colombo, Camilo DeLellis, Sezekelyhidi, Janish, and Hanji Kwon. Okay, so then there's new recent work by Elia, Anuj, and Maria, and even more recent by Alexei and Mimi. Okay, let me tell you why this p equals 3/2. Let me show you why this is such a natural critical exponent. So I'm going to give you a baseline result, which says that every weak solution whose vorticity is bounded in time to L3/2 conserves energy. Okay? And you even have a local energy balance law holding. Okay, let me give you the idea. The idea of the proof is really elementary. Basically, you take your Euler equations, you take the convolution of your Euler equations with a modifier. Here's what you get as a result. Okay, so now U epsilon, P epsilon, everybody's smooth, but you have an error term, R epsilon, which is basically the commutator between taking the convolution of the nonlinearity and the nonlinearity of the convolution. Okay? Okay, you multiply everything by U epsilon, which is now a smooth thing, and you want to show that each term converges to the right thing. Okay, the first term converges without any problem in this regularity assumption, and the second one also, and the third term, which comes from the flux term, U epsilon times the R epsilon, your error term, you want to show that it converges strongly to 0 in L infinity and time L1 in space. Okay, as I mentioned, A and B are subcritical for vorticities in L3/2, but they only require much less. They require vorticity in L6/5, but to get the convergence of the flux term, that's where you need the L3/2. And the reason is because the Sobolev embedding gives you that U is at L6, and so you combine everything and you get exactly the right, you just use Holder inequality, everything comes out just right. Okay? So the key fact here is that in L3/2, U, because of Calderon-Zygmunt, U times gradient of U belongs to L1. Okay? And the norm goes like W1 cubed. Okay? So this is exactly right. All right, so this tells us that every weak solution with a vorticity, which is L3/2, conserves energy, and you don't seem to be able to do any better. There's no room for improvement here. Therefore, we decided to look instead at vanishing viscosity weak solutions. These are special weak solutions, which are limits of solutions of Navier-Stokes. So we refer to these as physically realizable weak solutions. The name is supposed to evoke exactly what it does. Okay, that these are the correct weak solutions that you want to be looking at. So I'm going to call a weak solution which physically realizable if it's a weak solution of the Euler equations according to that other definition I gave you, and if it's a limit of Navier-Stokes solutions when viscosity goes to 0. Okay, and I will ask that the initial data converge strongly. Okay. A given family of Navier-Stokes solutions which satisfies this definition, which converges to this weak solution, will be called a physical realization. So, using this definition in joint work with Alexei Shashkinov and Roman Shvitkoy and Milton Lopes, we showed the first supercritical result of energy conservation for weak solutions of Euler, namely that if a physically realizable solution has a vorticity in LP for any p greater than 1, then it is conservative. It conserves energy. We don't know anything about local energy balance, though. Okay, p less than 3/2 is supercritical. Okay, I'm going to tell you a little bit about the proof. What time is it? Okay, we're doing okay. I'm sorry?
We have 10 minutes.
10 minutes?
Wait.
Okay, yeah, all right, that makes sense. Okay, so I'm going to tell you a little bit about the proof, basically because there's one aspect to which I want to zero in on. So what we do is we take a physical realization. Okay. We look at the entropy, which is the L2 norm squared of the vorticity. We use these embedding theorems and inequalities like Gallardo-Dierenberg, maximum principle, usual stuff, to get a differential inequality for the entropy. So the entropy, the total agent entropy, is bounded by minus a constant times viscosity times the entropy to a power that's greater than 2. This is the relevant fact. Okay? With this, we get an inequality. We then integrate in time, use Grunwald, integrate in time, and we get that the entropy will blow up when t goes to 0, but it blows up at a specified rate, which is namely nu times time to the power of minus 2 minus p over p. Okay, then we go back to the energy identity for Navier-Stokes. We rewrite it in terms of vorticity. We rewrite the dissipation term, which was minus nu times the integral of the grad of u squared. We rewrite that in terms of vorticity as minus 2 nu times the entropy. Integrate in time, use the estimate that we just got for the entropy, and we wind up with the energy at time t for the viscous solution minus the initial energy is less than or equal to 0, but it's greater or equal to a quantity which vanishes when viscosity vanishes. It's minus nu t to a power 2 times p minus 1 over p. And p is greater than 1, so this vanishes. And to conclude the argument, since the initial velocity converges strongly in L2 by definition, we only need to know that the energy, the viscous energies, converge to the Euler energy. And that's a consequence of work by Dupern and Maida from 1987, called the non-concentration result. Okay, so QED. What were the key steps in the proof? Show that the dissipation vanishes. For this, we needed to use a Grunwald lemma for a differential inequality with the right-hand side, which grows like a power greater than 2. And then use a strong convergence in L2 of the physical realizations. That was a non-concentration result. Just that. Okay. So we were very surprised to learn in 2021 that actually the dissipation term vanishing is a consequence of strong convergence. That's highly non-obvious. And this is work by Samuel and Haller, Sid Bishop, and Carlos Pares Pulido. They showed that these two things are equivalent. In fact, that strong convergence in L2 implies no anomalous dissipation, and therefore that implies that U is a conservative weak solution because of strong convergence also. Okay? And that this is equivalent. These two things are equivalent. Okay, I'm going to skip these consequences and tell you a little bit about adding forcing. We then looked at adding forcing, okay? Because forcing is a standard mechanism to generate small scales and therefore roughness in your fluid flow. So we wanted to know how irregular, how rough we could take the forcing and still get some kind of if and only if criterion for energy conservation. And we need to adjust the definition of physically realizable weak solution to include forcing. So we asked that the forcings converge weakly, L1 and time L2. And we have the following necessary sufficient condition, building on the work of Sid and Senna and Carlos Perez-Pulido. So this is work that appeared, I think, this year. That's work from last year, submitted last year. So a physically realizable weak solution of the Euler equations with some kind of external forcing, which is actually L2 in time, L2 in space, and converges strongly. Then you have, under these conditions, you have an if and only if criteria. U is energy balanced if and only if U converges strongly. U nu converges strongly. Okay. Let me skip the discussion of the proof. And let's abandon compactness now, because now what we're interested in are vortex sheets. Okay, so vortex sheets are way too rough for vorticities in LP. Their vorticity is actually a bounded measure. Okay? Therefore, we have no compactness. We don't expect any compactness in L2 of the velocity fields. Okay, so what can be done under these conditions? So now assume that your vorticity is either L1 and H minus 1 or a bounded measure and intersect H minus 1. And what you have to have in mind is a vortex sheet. Okay, so these spaces, as I mentioned, they're not compact in H minus 1, and therefore inviscid dissipation is possible. And the question now becomes, is anomalous dissipation possible? Okay, so let's consider Navier-Stokes solutions whose initial data converges at least weakly in L2. And then we have the following theorem, following result. There's two attributions. I need to tell you a little story about this. One is by DeLellis and Park. The other one is by Tarek El-Gindi, Lopes, and myself. Okay, and let me tell you what are the assumptions. So the red assumption is common to both papers. We need to have initial data converging strongly at L2, and the viscous vorticities need to be bounded in the space L infinity and time L1 in space. Okay, then you have some conditions on the forcing. These are technical conditions. And then this blue condition is also common to both papers. Okay, the supremum, it's a really weird condition as stated, but I need to explain to you what it means. So the sup in viscosity, the sup in time, the sup in center, Z, of the mass of vorticity in a little ball around Z of radius R, this has to vanish when R goes to 0. So I'm going to read this like this. My vorticities do not form atoms inside my flow. Okay, they don't form Diracks. I look at the absolute value of the vorticity. I look at this inside a little disk. Okay, and when the disk vanishes, this goes to 0. But it goes to 0 uniformly in viscosity and time. That's what this last condition says. Okay, under these conditions, you have no anomalous dissipation. Okay. Under the assumptions of the theorem, any weak limit of these Navier-Stokes solutions is a physically realizable weak solution of the 2D Euler equations. But note that this theorem refers to anomalous dissipation, therefore it refers to families of solutions of the Navier-Stokes equations. It doesn't refer really to the solution of the Euler equations. Okay? All right. What is this business about DeLellis and Park and then El-Gindi, Lopes and myself? Well, what happened was we'd been discussing this, or I had been discussing this with Tarek since, I think, 2023. And then we decided to finally get together, Milton and Tarek and I, in Princeton last year, around February, I think. We visited Tarek, and then we dotted our I's, crossed our T's, came back to Brazil and said, let's sit down and start writing the paper. A week after I got back from the US, I pick up my cell phone one morning and there's an email from Luigi and Jae-min saying, oh, we got this paper, we got this new result, maybe you might be interested. And I started reading it, I said, oh my God, that's our theorem. Okay, so that happens, okay? It's a really nice result, I like it very much. And we were scooped, but it turned out that our proof was completely different from their proof when we had additional information which they didn't have. So in the end we decided to write it up. This was independent work, it was generally independent work, and we decided to write this up, and now both papers are actually submitted. Okay, also our work treats forcings which theirs doesn't. The main thing is that our work relies on a new a priori estimate for solutions of Navier-Stokes, or limits vanished viscosity solutions, and also our work comes with a rate, or a rate of anomalous dissipation, which their work doesn't. Okay, so I'll start reminding you what is Nash's inequality in 2D. Nash's inequality in 2D states that the square of the L2 norm of a function is bounded by the L1 norm of said function times the L2 norm of the gradient of said function. Or, in other words, the square of the square is bounded by the product of the squares. Okay, so the first step is to start out with a refinement of Nash's inequality, where if you have a family of functions bounded in L1 and H1, okay, such that this family is bounded in L1 and no Diracs are available, are formed. So the supremum on the family and the supremum in centers of the mass of this function f in a small disk centered at z of radius r, this goes to 0 uniformly in the family and in the centers. Then I can find a superquadratic function upsilon, which is C1 and convex and increasing, such that upsilon of f L2 squared is bounded by the gradient of f L2 squared. So this is a refinement of Nash because even though the L1 squared norm isn't present here, it's sort of implicit because, I mean, it's bounded by k. And I can basically absorb this k into my function upsilon. Okay. This upsilon is constructed very explicitly. It's the square of the inverse of a concave increasing sublinear function, capital Phi. Okay, so what we do is we apply this refined, this is ours, this refinement is ours, and we apply this refinement of Nash to the family given by the viscous vorticities, parameterized by viscosity and time. Okay, we look at the dissipation term, the full dissipation term. This is not the dissipation rate, this is the full dissipation term measured from some time delta to t. And we write this differential inequality here. ddt of the dissipation term is bounded by this quantity on the other side, which comes from applying the Nash theorem. When nu goes to 0, x2 goes to infinity, phi is sublinear, I'm dividing by x2, this thing goes to 0. QED. Okay. I still need to analyze what happens with the dissipation from time 0 to time delta, but that's basically easy. That's just continuity, right? Continuity of the 2D Euler solutions. Okay. In the refinement of Nash's inequality, as I mentioned, we have a very explicit construction of our function upsilon. Here is the formula for assuming only f in L1. If I assume a little bit more about my family, if I assume that my family is formed by functions which can be written as a non-negative measure plus an LP function for some p greater than 1, then I can use this function phi, okay, which is x over 4th root of log x. And so when I divide by x, that function, I actually get a rate. I get that the dissipation term goes to 0 like log nu to the minus 1/4. Pretty nice. And there's no anomalous dissipation if you start in L1. Okay, so the answer is, if for vortex sheets, for all the vortex sheets for which we can prove existence of a weak solution, there's no anomalous dissipation. Okay, we have no idea if this is sharp, and we don't believe that this rate is sharp. We don't believe it is, but we don't know how to prove it. Okay, Finally, let's look at this. There's an example of possible anomalous dissipation when you form a Dirac, which is called phantom vortices. However, there's two things that are happening here at the same time. My flow is forming the vorticity is forming a Dirac in the middle of the flow, but the initial velocities don't converge strongly. So we don't know what is the relevant phenomena here, what it is that we really have to be excluding. Okay, let me give you a few conclusions. First off, this is a conclusion from our 216 paper already, that Onsager scaling is not the last word on inviscid dissipation, because we managed to prove that there is indeed a dynamical mechanism which avoids the inviscid dissipation in 2D. And the situation seems to be contrasting with the 3D situation, according to work by Maria Colombo, Gianluca Crippa, and Massimo Sorella from 2022, and then these other million authors from 2023. Okay, so we produced physically realizable weak solutions which conserve energy, and therefore, in particular, these solutions are not attainable by convex integration methods, because they do conserve energy, and the convex integration methods are designed to produce solutions which don't conserve energy. Okay. So we wondered if this was some kind of 2D selection criteria, and now there's this new work by Maria and Elia, which showed, and Julia, which showed that no, you don't have a selection criteria yet in 2D. The vorticity is an LP, P larger than 1, and there are two vanishing viscosity solutions. Okay? However, their work is in the presence of rough forcing, so we don't know. They are aiming at something with zero forcing, but so far, no go. Okay? And the plot thickens. Okay, in the case P equals 1, if you don't have compactness, we all believe that that we cannot prove energy conservation, okay, that inviscid dissipation is possible, but we have no idea how to prove this. We have no tools, okay. I want to point out that there's a discrepancy between this and the knowledge we have on how the vorticity behaves in this case. And so we decided to go for a less ambitious project, take an initial vorticity in L1 and know better than L1. In other words, do not assume that you have energy conservation. Do not assume that you have strong convergence of velocities. Take a physically realizable weak solution. Is this attainable by convex integration? We don't know. Okay. Another observation is that vorticity transport in incompressible fluid flow is a relevant physical restriction that is ignored by wild solutions. And basically because the vorticity is too irregular. And even the current great, fantastic new results on non-uniqueness in LP, they don't give us vorticity transport because P is too close to 1. When P is too close to 1, you can't really talk about vorticity transport. So in order to be able to talk about vorticity transport, you need the vorticity to belong to LP for some P greater than 4/3. So it's an open question whether you have non-uniqueness of physically realizable solutions with vorticity transport. Okay, so I'm going to close with a musing dedicated to Carlos. One day, you're 20 in the 70s. Next day, you're 70 in the 20s. Happy birthday, Carlos.
What does it physically realizable mean now?
What does?
Experiments here.
I'm sorry, could
In the last slides, there was a question of whether something is physically realizable. What does that mean? Are you going to do an experiment?
No, physically realizable means it's a solution that comes from Navier-Stokes, from real fluids.
From Navier-Stokes?
Yes, because Euler is a figment of my imagination, right? I mean, a solution of the Euler equations with the fluid has no viscosity, this doesn't exist. But it's a natural question to ask whether you can indeed neglect viscosity, okay, ignore it. And the answer to that question is the same as asking whether you can take vanishing viscosity limit and get a solution of the Euler equations. The same thing.
Oh,
Yes.
Helena, this is for someone who is try to be smooth like me. This is awesome. I can't cope with that. However, I would like to ask a question in the spirit of geometry. How much this analysis would go if your underlying metric is non-Euclidean? Nothing changes, or it should be different?
Okay, so I don't think a lot will change because you do have a lot of results for vortex sheets on manifolds, for instance. Yeah, on differentiable manifolds. Yeah, I don't think a lot will change.
It should go through. Good.
Yeah, it's an issue of regularity, not an issue of geometry.
I have two naive questions. The first one is the following. You say that this journey starts in the 09 with Camillus and Laszlo paper introducing the convex integration. So they start in dimension 3 to produce this mechanism, and later pass to dimension 2. What is the abstraction? Is dimensional, topological, or?
Dimension 2, you don't have enough space.
Okay, so at the end you depend on the.
You need space. You need space to move around. Okay, you need space to move around. It's just that. Okay, so all of these constructions, they use these very special flows like Beltrami flows, Mikado flows. All right, these flows need space to be able to move them around. Okay, so there was a large gap, a large time period before you could actually make things work. Find the right flow to make things work in 2D. And no, I don't know what that is. I haven't read their paper yet. It came out last year.
Okay, so you need the space then.
Yes.
Okay. And the second is more a curiosity. You talk about the Schaefer solution. What is the regularity of Schaefer's solution in 95?
The regularity is, it's just, the velocity is just L2, L2. L2 in time, L2 in space. Square integral, just that.
Okay.
You know, nothing additional about it.
Okay.
And it's really, really rough.
Okay. So thank you.
Yeah, one question. This flow you mentioned that takes bothers Idris TT at night.
Can you refer? I'm sorry. I'm very hard of hearing these days.
This flow that you said that takes bothers Idris TT at night.
Yes. Okay.
Seltzer kind of flow, right?
Yeah, the compactly supported flow.
What triggers it from rest?
This is a completely ad hoc construction.
Yeah, but what triggers it from rest?
Okay, there's nothing that triggers it because this is not it's not a physical construction. Okay, this is completely ad hoc and it's basically exploring a defect in the definition of a weak solution. It's just that.
Yeah, but even from the
if you want,
point of view, what triggers it?
if you want, okay, the original, the Sasha Schnirelman's construction, which came much before that, okay, that construction was inspired on this idea of the forward entropy cascade and the inverse energy cascade. Okay, that is a physical phenomenon.
But the inverse energy cascade, energy is coming from somewhere.
Yes.
Small scales, right?
From the small scales, exactly.
And
Well, if you want, something is coming from small scales but basically what you're doing is you're adding lots and lots of oscillations.
if it's coming from small scales, it was present, right, at time zero.
No. No, you're just exploring, weak convergence. It's more physical. And that is the main criticism.
I'm just thinking purely from equation point of view. Whatever. Definitely it's not physical. This kind of Alka-Seltzer is a nickname.
No, it's an abstract construction, and it's, in the beginning it was just exploring this defect in the definition of weak solution.
And this anomalous energy dissipation is present in all scales.
We don't have anomalous energy dissipation.
No, but in the case where there is a not this.
You have inviscid dissipation.
Sorry?
You have inviscid dissipation.
Yeah, well, this is missing.
Yeah.
Anomalous this.
Okay.
In that sense, it takes place with all scales present in the model.
Sure.
Okay, let's have clock grading up to 4 p.m. and then the conference call will.